I welcome you all to our next lecture in the series of lectures in advanced power electronics. Today we resume our lecture on boost converter. In the last lecture we had discussed boost converter in continuous conduction mode, and we had designed inductor and capacitor based on the circuit based on the desired ripple in inductor current and capacitor voltage. Today we will discuss the converter operating in discontinuous conduction mode, that is when the inductor current becomes discontinuous due to some reasons, which those reasons also we'll discuss towards the later half of this lecture. So in this lecture we are going to discuss discontinuous conduction mode, why it happens, and what are the consequences of discontinuous conduction mode, just like we had discussed for the buck converter circuit. First, let's move to the consequences, that when DCM happens, what are the adverse effects of discontinuous conduction mode in the boost converter circuit. For now, from the analysis that we have done previously, we know that in continuous conduction mode, the output voltage of the converter V0 is equal to VDC upon 1 minus D, where D is the duty ratio, or the ratio of turn on time upon the total switching interval of the device used in the converter circuit. So this is the expression for continuous conduction mode. Let's see that let's assume that the inductor current becomes discontinuous. So if the inductor current, we know that when the switch is on, the inductor is storing energy and the inductor current is rising. So from 0 to DTS, the inductor current is rising, and then from DTS to TS it was falling, but because we are considering discontinuous conduction mode, it falls sooner. It releases energy quickly due to a number of reasons that have to do with the design of the inductor, the switching frequency, the load, etc., etc., the duty ratio itself. The many factors will affect this. So due to some factors, what are those factors, we'll come to that later, but due to some factors, the inductor current has become discontinuous sooner than TS, say at beta TS. Now let's analyze the circuit for all these intervals, that is 0 to DTS, DTS to beta TS, and beta TS to TS. Now let's see 0 to DTS. What happens is that the inductor is storing energy through the switch. The pulse to the switch is high and the diode is reverse biased, and the voltage across the load is being maintained by the help of a capacitor. So the capacitor is discharging and losing energy into the load. The voltage across the inductor is VDC, as the inductor is directly connected across the source. The switch is conducting, so the voltage across the switch is 0. The diode is not conducting, so voltage across the diode, that's how you've connected, is it's minus of V0. If you apply KVL over here, the minus sign implies that it is blocking negative voltages. Well and good, because it can block only negative voltages. Moving on to DTS to beta TS. So now you have withdrawn the pulse to the device, and the inductor will now switch its polarity, and it will start releasing energy through the freewheeling diode. It will forward bias the freewheeling diode or fast recovery diode and dump energy into the capacitor and the load. Now let's observe the circuit in this interval. We have the inductor, the fast recovery diode, the switch here is open because you have withdrawn the pulse, the capacitor and the load in the circuit. So let's quickly see the voltage across the inductor in this interval. It has to be VL is equal to VDC, and this is V0, so it is VDC minus V0. What about the freewheeling diode? It is conducting, so voltage across it is 0, the fast recovery diode, and voltage across the switch in this interval, it is not conducting, so it is supposed to block some voltage, and that voltage is directly the load voltage V0 plus V0, because it is directly connected across the load. This switch is directly connected across the load. So these are the parameters during energy releasing interval in discontinuous conduction mode. These are for energy storing interval. And then at beta Ts, it is known that the inductor has lost all its energy. It is not associated with any current. And when the inductor has lost all its energy, it will cease to forward bias this diode. So the diode will be reverse biased, and the switch is already off because you do not have the pulse. The diode is off because the inductor will not forward bias it anymore, and because the load voltage is greater in magnitude than the source voltage, it will ensure that the diode is reverse biased. The circuit will look something like this. So this is your load, and this is how your circuit will look like. And also, since there is no current flowing through the inductor because it is not associated with any energy, the voltage across this inductor will also become zero. Now if we analyze, this is beta Ts to Ts. So if we analyze for these parameters, we have voltage across the inductor is 0, and we have voltage across the diode. Let's see what voltage across the diode is. If we apply KVL over here, it is VDC plus 0. VDC is equal to 0 plus voltage across diode plus V0. So voltage across diode is VDC minus V0 in this interval. And then from if you want to see the voltage across the switch, which is this voltage, we can simply say that it is VDC, because the switch is directly connected over here across the source, because this voltage is 0. So this is VDC, and this voltage is VDC minus of V0 if we apply KPL here. So this was from the interval beta Ts to Ts. If we quickly do the volt second balance, we will see that some changes happen in the output voltage of the converter. So these are the three intervals. Now let's try to do the volt second balance. This is the first interval, the second interval, and the third interval. From volt second balance, we have that we know that the voltage, the product of voltage and time for an inductor should be 0. The summation of all those products over an interval should be 0. So in the first interval it is VDC, and the interval duration is DTS. Then in the second interval it is VDC minus V0, and the interval duration is beta Ts minus DTS. And then in the last interval it is 0, so you can just simply equate all of this to 0. So we have, if we solve further, we have dVDC plus beta times VDC minus beta times V0 minus D times VDC plus D times V0 is equal to 0. So dVDC goes, and V0 is equal to, if we take this there, it is beta times VDC upon beta minus D. So this is your equation, right? I want to manipulate it a bit. I can write it as V0 is equal to VDC upon 1 minus D upon beta. So you know that in discontinuous conduction mode, this is your expression for V0, and in continuous conduction mode, your expression for V0 was V0 in CCM, which we had done in the previous lecture, was VDC upon 1 minus D. Now you have the factor D upon beta. Let's see how it will affect the average output voltage. If you have beta, which is a fraction, you're dividing it by something. So the whole thing is increasing. This particular fraction is increasing. This overall whole thing is decreasing, and the whole fraction is increasing. So you know that V0 DCM is greater than V0 of CCM, which is again undesirable, because you know that your devices are stressed to V0 in case of a boost converter circuit, they are stressed to the load voltage. अगर आप diode या switch अपना खरीदते हो, you purchase them from the context of the output voltage that that the circuit has to produce. Now if you have a 5 volt input and you're producing a 20 volt output, you would assume that your diode and your switch will be rated at 20 volts. But if your converter goes into DCM, which is discontinuous conduction mode, it is likely that your converter output may be say 50 volts or 30 volts depending upon the value of beta, and as a result of which there is some possibility that you may damage your devices. Forget about damaging, you're also having unexpected behavior from the converter. You may be you may even damage your load for that matter. You may be charging a battery at 12 volt, but you may exceed the voltage by venturing into DCM, and if you're not careful enough, you may not probably even know that you're going into DCM. So for that, you need to know that what factors lead you into DCM, and you have to ensure that you do not go into discontinuous conduction mode. Now what factors lead you into that? That is the boundary condition between DCM and CCM. So let's move to the boundary condition between DCM and CCM. So we know that DCM and CCM is determined by the inductor current. Now your inductor current can be in CCM, right? So this is your inductor current in CCM, and assuming the same peak inductor voltage, your inductor current when it goes into DCM, it will look something like this. So the average inductor current will be IL average in DCM, and IL average in CCM is greater than IL average in DCM. So for CCM, you have to ensure that the average inductor current for CCM to happen, that the average inductor current should be greater than or equal to the inductor current at the time of the boundary condition, which is just continuous. Say, let's show it by this. Let's show it by a dotted line, or maybe by this shaded line. So this is your boundary condition where your current is, you can say, neither continuous nor discontinuous. It's hitting 0, but it is hitting it at TS. So this is DTS, and then this is TS, and this is beta TS if your current is discontinuous, right? So at boundary condition, your current is just continuous, you can say, something like this. It's a triangle, and the peak to peak ripple is, if we say that the peak to peak ripple is delta IL, then the average inductor current at the time of boundary, let's call it ILP, will be equal to delta IL by 2, right? For CCM, your inductor current should be greater than or equal to delta IL by 2. Obviously, when it is equal to delta IL by 2, at that point in time, your inductor will be at the boundary, will be neither continuous nor discontinuous, or you also call it just continuous. So this is the condition for CCM to happen. Now let's manipulate this equation a little bit. If we see the boost converter circuit during energy storage interval, so let's forget that part, we have L di by dt, that is voltage across the inductor, it is equal to VDC. So delta IL is equal to VDC in the interval DTS, 0 to DTS, if I'm using this equation over here, VDC into DTS divided by L. So my inductor current should be greater than equal to VDC DTS upon L. Moving on further, you have inductor current should be greater than equal to, if I write this VDC in terms of V naught, it should be V naught into 1 minus D into D TS upon L. Now, the inductor current itself is a source current for a boost converter circuit. If you see the boost converter circuit, the inductor current is a source current. So VDC into inductor current should be equal to V naught into load current I naught. So that is input output power balance. जितना power source से गया उतना ही power load में consume हुआ. Assuming it's a lossless converter, there are no losses anywhere here. Using that assumption, we can say that IL is equal to V naught I naught upon VDC, and we know that V naught is equal to VDC upon 1 minus D. So this is VDC over here and this is I naught, this goes. So IL is equal to I naught upon 1 minus D. So I can write it as I naught upon 1 minus D. जो सेम रिलेशनशिप V नॉट और VDC के बीच में है उसी की इनवर्स रिलेशनशिप है ये, बिकॉज इफ you're boosting voltage at the other end, you're boosting current at the input end. So that's basically, this current is a boosted version of I naught. The source current is a boosted version of I naught that is expressed here. And I can write this as D into 1 minus D TS upon L. इस V naught I naught को मैं V naught upon R भी लिख सकती हूँ. So we can cancel out the two V naughts, and from here we have, there was also a 2 because it was delta L by 2, तो वो सारा 2 भी होगा कहीं पे. Okay, then we have 2L by R TS should be greater than or equal to D into 1 minus D whole square. So this is your boundary condition for CCM. So for CCM to happen, this, your inductor should be big enough, or your resistor should be small enough, or your switching frequency should be high enough so that this whole term becomes greater than or equal to D into 1 minus D whole square. Let's try to see this graphically. If we observe it by means of a graph, say this is my changing duty ratio, because mostly when you operate the converter, you operate it for a fixed switching frequency with a fixed load and a fixed inductor. So the variable term is usually the duty ratio. Now when you're changing the duty ratio, obviously 2L by RTS, or you can say 2L FS by R, is going to be constant. It's not going to change. But this thing, the right hand side of this equation, that is the equation for CCM to happen, is D into 1 minus D whole square. So at D is equal to 0, this term is 0. At D is equal to 1 also, this term is 0. And it has 1 minus D whole square curve. So this curve is going to look like this. So this is my curve for D into 1 minus D whole square. Now, as long as 2L by RTS is greater than D into 1 minus D whole square, your converter is in CCM. So your converter is in CCM. Here, when 2L by RTS is greater than this, and here when 2L by RTS is greater than the curve, so this is also CCM. But in the middle part of the curve, your converter is in DCM, because 2L by RTS is equal to D into 1 minus D whole square. Now let's see. If let's see this, we saw the equation, we derived the equation, we saw it graphically. Now let's see it graphically. अगर आप inductance को बढ़ाओगे, ठीक है, तो ये ये लाइन आपकी ऊपर ऊपर जाएगी. दिस लाइन विल गो हायर एंड हायर, एंड एज दिस लाइन विल गो हायर एंड हायर यू विल गेट continuous conduction. See, you will get continuous conduction for larger values of D, right? Similarly, अगर आप स्विचिंग फ्रीक्वेंसी को बढ़ाओगे या आर को घटाओगे, ये लाइन ऊपर ऊपर जाएगी, आपको ज़्यादा चांसेस हैं कंटिन्यूस कंडक्शन मोड मिलने के. दैट मीन्स इफ़ यू इंक्रीज इंडक्टेंस, इफ़ यू रिड्यूस रेजिस्टेंस, और इफ़ यू इंक्रीज स्विचिंग फ्रीक्वेंसी, ऑल दीज थिंग्स विल गिव यू greater likelihood of having continuous conduction mode over a wide range of D. और अगर अब आप D के टर्म्स में देखो तो you also know that smaller Ds and larger Ds, very small Ds and very large Ds will give you CCM, but middle portion में it is likely to go into discontinuous conduction mode. सीधी सी बात है, अगर हम इस चीज़ को we want to analyze it physically, एक intuitive तरीके से देखना चाहें, तो this is your boost converter circuit. एंड हायर इंडक्टेंस यानी कि आपकी इंडक्टेंस जो है वो धीरे धीरे एनर्जी स्टोर करेगी और धीरे धीरे एनर्जी रिलीज करेगी. द चेंज इन करंट थ्रू इट विल बी वेरी स्मॉल, एज अ रिजल्ट ऑफ विच योर inductor will your converter will go into CCM, continuous conduction mode. Higher switching frequency पे काम करोगे तो obviously again the inductor will be subjected to very high switching frequency. When it's subjected to very high switching frequency, इस very high rapid variations और very high switching की वजह से आपके कन्वर्टर की जो करंट्स हैं उसमें बहुत हाई वेरिएशंस इन मैग्नीट्यूड नहीं हो पाएंगी. हाई मैग्नीट्यूड वेरिएशंस थोड़ी थोड़ी चेंजेस ही होंगी क्योंकि इंटरवल्स बहुत छोटे हैं, राइट? दैट इज़ योर हाई स्विचिंग फ्रीक्वेंसी. सो इट विल मेक श्योर कि छोटी चेंज आए आपके इंडक्टर करंट में, बिकॉज द इंटरवल ऑफ स्विचिंग इज़ वेरी स्मॉल और योर स्विचिंग फ्रीक्वेंसी इज़ वेरी हाई. Similarly, if you have a very small value of resistance, it will make your time constant very high, your L by R ratio very high. So there will be a slow release of energy, a slow discharge of energy into the load, because of which your continuity of your inductor current will be maintained in the second half interval when it is supposed to release energy. अब बात आती है duty ratio की. There is something interesting that I want to focus upon. That is your how the duty ratio, if we see it physically, how the duty ratio affects your converter and makes it go into CCM DCM. हम ये जानते हैं कि अगर आप बूस्ट कन्वर्टर देखो और अगर आप बक कन्वर्टर देखो, which you have previously done, बूस्ट कन्वर्टर में कर्व कुछ ऐसा है, ठीक है? So this is your 2L by RTS, and this is, it should be greater than D into 1 minus D whole square. And if you see your buck converter, and this is your D, right? If you see your buck converter circuit, the curve was like this, and this was your 2L by RTS. So it, as long as it was greater than 1 minus D, your converter was in CCM, and otherwise it was in DCM. Here your converter is in CCM at the two extremes and in DCM over here. अब common sense से अगर हम if you see through common sense, हम कहते हैं कि अगर एक buck converter circuit है, so this is your buck converter circuit, during the energy storage interval your inductor stores energy when the switch is on, and when the switch is off it releases energy through this loop, right? लेकिन इस सर्किट में क्या है कि अगर छोटा ड्यूटी रेशियो होगा तो आप बहुत कम देर तक इंडक्टर एनर्जी स्टोर कर पाएगा फॉर अ गिवन एल. आई एम टॉकिंग अबाउट वन पर्टिकुलर वैल्यू ऑफ एल एंड वन पर्टिकुलर वैल्यू ऑफ एल आर टी एस, ऑल ऑफ दोज. अब हम सिर्फ ड्यूटी रेशियो के टर्म्स में बात कर रहे हैं. अगर छोटा एल है तो छोटा d है तो the inductor will store energy for a small interval of time, and then it is more likely that if dts to ts is a large interval, obviously it's more likely that the current will become discontinuous. And if you don't want the current to become discontinuous, then you will have to have a very very high value of L, और switching frequency बहुत ज़्यादा बढ़ानी है या लोड की resistance बहुत कम करनी है. But for some standard values of LRTS, it is likely that अगर आपका D छोटा हुआ तो बहुत देर तक energy release करना possible नहीं है. It most likely it's going to release energy somewhere before TS, and small duty ratios will contribute to discontinuous conduction mode. और जैसे जैसे आप अपना ड्यूटी रेशियो बढ़ाओगे तो ज़्यादा देर तक एनर्जी रिलीज करेगा. इट्स मोर लाइकली दैट योर कन्वर्टर विल रिमेन इन CCM. योर इंडक्टर करंट विल नॉट डीके बाय द टाइम यू रीच द नेक्स्ट स्विचिंग साइकिल. सीधी सी बात है, इट्स कॉमन सेंस, इट टेल्स यू दैट. सो दिस इज वैलिडेटेड इंट्यूटिवली ऑल्सो. नाउ इफ यू सी दिस सर्किट, the boost converter circuit. So this is the boost converter circuit. This is the diode, capacitor and the resistor. इसमें क्या होता है, इसमें छोटे सी पे तो CCM आ जाता है, विच इज़ अनलाइकली. छोटा, बहुत छोटा ड्यूटी रेशियो जब होगा, यू विल से दैट वेरी स्मॉल ड्यूटी रेशियोज, इट मीन्स दैट it's likely that your inductor could not store enough energy. फिर वो इतनी देर तक एनर्जी कैसे रिलीज करेगा? Now I'll tell you why in very small duty ratios you still get CCM in a boost converter. What is the difference? बहुत छोटे Ds की बात करते हैं हम. जब इंडक्टर को एनर्जी स्टोर करनी है, it gets directly connected in a boost converter circuit. It gets directly connected across the सोर्स. यानी कि इसकी पाथ में बहुत कम रेजिस्टेंस है, वो जो इंटरनल रेजिस्टेंस होगी इसकी, विच यू कैन निगलेक्ट एंड यू कैन से इट ऑलमोस्ट इंस्टेंटली, बहुत ही छोटे इंटरवल में भी ये बहुत ही ज़्यादा एनर्जी लूज करेगा, गेन करेगा. इट विल स्टोर अ लार्ज अमाउंट ऑफ एनर्जी इवन इन वेरी स्मॉल ड्यूटी रेशियोज, राइट. और फिर जब आप DTS तक से TS तक जाओगे, रिलीज इसको एनर्जी जब करनी है, उस रिलीज के पाथ में आपकी रेजिस्टेंस आ जाएगी, उस रिलीज के पाथ में कैपेसिटर भी है. तो जब रेजिस्टेंस भी आएगी, द रिलीज ऑफ एनर्जी विल बी स्लो, एज अ रिजल्ट ऑफ विच स्मॉल ड्यूटी रेशियोज पे भी आपको CCM मिल सकता है, राइट. ऑन द कॉन्ट्ररी, इफ यू सी स्मॉल ड्यूटी रेशियोज फॉर अ बक कन्वर्टर सर्किट, जब बक कन्वर्टर को एनर्जी स्टोर करनी है, उसकी एनर्जी स्टोर करने के पाथ में भी आपकी रेजिस्टेंस आ रही है. सो इवन स्टोरिंग ऑफ एनर्जी इज वेरी स्लो इन अ बक कन्वर्टर सर्किट. यानी कि अगर आपने बक कन्वर्टर को छोटे ड्यूटी रेशियो पे ऑपरेट किया, तो इट इज़ लाइकली इट विल स्टोर एनर्जी एंड वेरी लेस एनर्जी, क्योंकि कम इंटरवल है और ये जल्दी एनर्जी नहीं स्टोर कर रहा है. इट्स स्टोरिंग एनर्जी वाया द रेजिस्टेंस इन इट्स पाथ. सो इट्स स्टोरिंग एनर्जी स्लोली एंड देयरफॉर इन अ स्मॉल इंटरवल इट हैज़ नॉट स्टोर्ड इनफ एनर्जी एंड इट्स ऑल्सो रिलीजिंग इट थ्रू द रेजिस्टेंस पाथ. तो रिलीज करने में भी स्लो ही है, पर एनर्जी ही कम स्टोर हुई है, तो ये पहले ही ख़त्म हो जाएगा. यहाँ पे बेनिफिट था कि इसने कम इंटरवल में बहुत ज़्यादा एनर्जी स्टोर कर ली थी, इसने उतनी ज़्यादा एनर्जी स्टोर नहीं की है, और ये रिलीज धीरे धीरे करता है. ये स्टोर और रिलीज ऑलमोस्ट सेम पाथ पे कर रहा है. सो फॉर स्मॉल ड्यूटी रेशियोज यू गेट CCM हियर, राइट. दैट इज वाई इट हैपन्स, बिकॉज ऑफ द सर्किट डिफरेंस. एट हायर ड्यूटी रेशियोज तो दोनों में पता ही है, जितना हाई ड्यूटी रेशियो होगा, बहुत देर तक एनर्जी स्टोर की होगी, तो ऑब्वियसली बात है दैट इट विल बी इनटू CCM. सेम केस ओवर हियर, वेरी हाई ड्यूटी रेशियोज. Now the difference lies in the middle path. कि आप बूस्ट कन्वर्टर सर्किट में देखते हो कि आपको बीच में कहीं पे DCM मिल जाता है. Somewhere in the middle you get discontinuous conduction mode. Let's try to understand that physically. So this is your boost converter circuit again. Let's talk about somewhere in the middle DTS and this is DS. एक moderate सा duty ratio middle में, we know that middle में DCM होने की chances है. Let's understand why. 0 से DTS तक आपके इंडक्टर ने एनर्जी स्टोर की, और बहुत तेज एनर्जी स्टोर की, बिकॉज इट वॉज डायरेक्टली कनेक्टेड अक्रॉस द सोर्स एंड देयर वाज नो रेजिस्टेंस वाया विच इज टू स्टोरिंग एनर्जी. सो इट स्टोर्ड अ लार्ज अमाउंट ऑफ एनर्जी. आइडियली स्पीकिंग इट शुड सीम लाइक व्हेन यू स्विच दिस ऑफ, जब आप इसको स्विच ऑफ करोगे तो आपका इंडक्टर जो है इट शुड रिमेन इन CCM. छोटे ड्यूटी रेशियो पे रहा तो उससे ज़्यादा मॉडरेट ड्यूटी रेशियो पे क्यों नहीं रहेगा, राइट. बट देयर इज अनदर थिंग इन टू प्ले, and that is your capacitor voltage. अगर आप कैपेसिटर वोल्टेज की बात करो या V0 की बात करो, पहले आपके पहले इंटरवल में कैपेसिटर इज लूजिंग एनर्जी, and then it is gaining energy. हमने पहले भी we have done that. It's not the boundary condition we are talking about. we are talking about normal. अगर हम assume करते हैं कि आपका कन्वर्टर CCM में है, तो पहले आपका कैपेसिटर रिलीज करेगा एनर्जी, देन इट विल गेन एनर्जी. नाउ जैसे जैसे आप डी को बढ़ाते हो, वैसे वैसे आपका जो कैपेसिटर है वो ज़्यादा ज़्यादा एनर्जी लूज करता है. हायर ड्यूटी रेशियोज पे इट इज़ पॉसिबल दैट योर कैपेसिटर वोल्टेज हैज़ फॉलन ड्रास्टिकली और द कैपेसिटर एनर्जी हैज़ बीन लॉस्ट ड्रास्टिकली. तो हायर ड्यूटी रेशियो, सपोज मिडिल ड्यूटी रेशियो पे कैपेसिटर की एनर्जी काफ़ी फॉल हो गई होगी. ठीक है, बहुत फॉल होने की वजह से जब फिर आप स्विच को ऑफ करोगे तो इंडक्टर को एनर्जी देनी है टू द रेजिस्टर एंड टू द कैपेसिटर. दिस कैपेसिटर इज हेविली डिप्राइव्ड ऑफ एनर्जी. इट विल ड्रॉ वेरी हाई मैग्नीट्यूड करंट एट दैट पॉइंट बिकॉज इसकी एनर्जी बहुत लूज हो गई है, एंड इट विल क्विकली सिंक इन ऑल द एनर्जी ऑफ द इंडक्टर, बिकॉज ऑफ विच द इंडक्टर विल क्विकली डिस्चार्ज. यहाँ सिंक मिलेगा इसको. यानी कि मॉडरेट ड्यूटी रेशियोज पे इट इज लाइकली दैट यू विल गो इनटू DCM. अब अगर वापस हायर ड्यूटी रेशियो की तरफ जाओगे, बहुत हाई ड्यूटी रेशियो की तरफ, ऑब्वियसली तब भी कैपेसिटर की वोल्टेज बहुत फॉल हो गई होगी, उसमें बहुत एनर्जी डेफिसिट प्रोड्यूस हो गया होगा, लेकिन उस टाइम तक आपके इंडक्टर ने बहुत ज़्यादा एनर्जी स्टोर करी होगी. फिर इट कैन सस्टेन फीडिंग द कैपेसिटर एज वेल एज द रेजिस्टर. तो देर आर टू कॉन्ट्ररी फैक्टर्स इन प्ले कि ज़्यादा देर तक ज़्यादा ड्यूटी रेशियो लो तो उसकी वजह से आपका इंडक्टर ज़्यादा एनर्जी स्टोर करता है, लेकिन एट द सेम टाइम ज़्यादा ड्यूटी रेशियो पे आपका कैपेसिटर जो है वो ज़्यादा एनर्जी लूज भी करता है. एंड व्हेन द कैपेसिटर लूजेस मोर एनर्जी इट विल क्विकली सिंक इन लॉट ऑफ एनर्जी फ्रॉम द इंडक्टर. दैट इज़ वाई द ट्रेड ऑफ इज कि बीच वाले ड्यूटी रेशियोज पे आपको DCM मिलता है और एक्सट्रीम दो साइड्स पे आपको CCM मिलता है. This is slightly tricky to understand, but if you analyze the circuit well, I hope you can understand this part. So this was about boundary condition between DCM and CCM for a boost converter circuit. Now, if you see, we want to discuss briefly the non-ideal boost converter. जहाँ हम कोई भी एक नॉन आइडियलिटी को मॉडल करेंगे, प्रेफरेबली द इंटरनल रेजिस्टेंस ऑफ द बूस्ट कन्वर्टर. इंडक्टेंस, दिस इस इंडक्टेंस की जो इंटरनल रेजिस्टेंस है, लेट्स डिनोटेड बाय स्मॉल r. देयर कैन बी अदर नॉन आइडियलिटीज लाइक द लीकेज रिएक्टेंस ऑफ द लीकेज करंट ऑफ दिस स्विच व्हेन इट इज ऑफ, द ड्रॉप अक्रॉस द स्विच व्हेन इट इज ऑन. Similarly, leakage current of the diode when it is off and drop across it when it is on. But for now, we are not modeling those things. For now, we are just modeling the internal resistance of the inductance, boost inductance. Now, during the energy storage interval, this switch is on and this is off. So, voltage across the inductor is VDC माइनस इंडक्टर करंट जो इसमें ड्रॉप प्रोड्यूस करेगी. दैट्स इट, एंड द लूप क्लोजेस, राइट. आई ऑल्सो वॉन्ट टू चेक द कैपेसिटर करंट. IC, it will be minus of I0 in this interval, if this is how I have defined I0, right. This is the first interval 0 to DTS. Now let's move to the second interval, that is DTS to TS, when the switch is off and this inductor will forward bias the diode and conduct in this path. उस टाइम पे आपकी voltage across the inductor क्या होगी? It will be VDC minus, this is the path of current, minus the drop across the internal resistance of the inductor. अगर आप इसका ड्रॉप मॉडल करते तो वो भी माइनस करते. We are not modeling it for now. And then minus of V0, because that's how the circuit is getting completed. So minus of V0. What about the capacitor current? It is IL minus I0. Right? पहले मैं आपको इसको सिंप्लीफाई करने के लिए पहले हम कैपेसिटर करंट्स के साथ we apply the capacitor current second balance. That is minus I0 DTS plus IL minus I0 1 minus D Ts is equal to 0. So minus di naught plus il minus I naught minus dil plus di naught is equal to 0. So minus di naught plus di naught goes, and we have I naught is equal to il 1 minus d. il is equal to I naught upon 1 minus d. ठीक है, ये आपने पहले ये इक्वेशन अभी थोड़ी देर पहले हमने इनपुट आउटपुट पावर बैलेंस से भी लगाई, लेकिन यहाँ हमने ये इक्वेशन कैपेसिटर करंट सेकंड बैलेंस से लगाई है, बिकॉज हियर इट डजंट मेक सेंस टू यूज द इनपुट आउटपुट पावर बैलेंस बिकॉज देर इज़ नो इनपुट आउटपुट पावर बैलेंस. यहाँ पे आपके इस रजिस्टर में लॉस होने वाला है. तो अभी हमने सिंपल कैपेसिटर करंट सेकंड बैलेंस से आई और आई नॉट के बीच में रिलेशनशिप निकाली. नाउ let's use the capacitor the inductor volt second balance. So we have VDC minus ILR for DTS, and then the inductor voltage is VDC minus ILR minus V naught for the interval 1 minus D TS, and this whole thing is 0. Now if we solve this further, we can say that let me solve it over here. I have dVdC minus DILR plus VDC minus ILR minus V naught minus dVdC plus DILR plus dV naught is equal to 0. Let's see, this and this goes. What else goes? Plus DILR minus DILR goes. अब यहाँ पे IL जो रहता है इसमें I want to substitute I naught. So I can call it I naught upon 1 minus D into R minus V naught plus dV naught is equal to 0. I can also write over here V naught upon load resistance R. So if I just manipulate a little more, I get VDC V naught is equal to VDC upon 1 minus D plus R upon R 1 minus D. Or I can say 1 minus D into VDC, and this becomes 1 minus D whole square plus R upon R, right? Now your output voltage equation for a non-ideal boost converter is this. If you neglect the resistance, internal resistance, assuming that it is very slow as compared to the load resistance, very small as compared to the load resistance, then you can just neglect this term and you simply get V naught is equal to VDC upon 1 minus D, which is your standard buck converter circuit. But as your internal resistance increases, you can see that voltage across the output of the converter, it actually decreases. And if you plot it, let me plot V naught, the curve for V naught. If we plot it at duty ratio equal to 0, this term will be 1 and this will be 0. The voltage will be V naught will be equal to VDC at D equal to 0. It will be VDC upon 1 plus R upon R. So that is duty ratio equal to 0. पहले आपकी VDC हुआ करती थी, अब VDC से हल्की रिड्यूस्ड है बिकॉज ऑफ दिस टर्म, because of the losses in the internal resistance. So this is VDC into 1 plus R by R. And at duty ratio equal to 1, your output voltage of the converter is in fact equal to 0. So duty ratio equal to 1 पे आपकी voltage fall होती है. The curve is something like this of a practical boost converter. Ideal क्या था? Ideal was hitting infinity at 1. But practical boost converter circuit says that in a practical boost converter, you will go on, as you go on increasing the duty ratio, you will go on increasing the output voltage to the converter greater than the input until it reaches a peak. From there, it will fall. And at duty ratio equal to 1, the voltage across the converter will become 0. Right? That is your practical boost converter circuit. Now, what is this value? कि ये पीक किस वैल्यू तक जाएगा, क्या मैक्सिमम आप कन्वर्टर से एक्सट्रैक्ट कर सकते हो, और किस ड्यूटी रेशियो पे ये पीक आएगा. लेट्स कॉल इट डी मैक्स एंड वी नॉट मैक्स. इनके क्या वैल्यूज होंगे? दैट इज सिंपल मैथमेटिक्स. फाइंड द मैक्सिमम ऑफ दिस कर्व. मैक्सिमम ड्यूटी रेशियो कहाँ पे होगा? जहाँ पे डी वी नॉट बाई डी 0 के बराबर होगा. सो डिफरेंशिएट दिस एंड इक्वेट इट टू 0. यू विल, let's quickly do that. We have 1 minus d whole square plus r upon r into minus of VDC. So this is minus of this. Minus 1 minus d into VDC into 2 times 1 minus d whole square minus का यहाँ पे plus हो जाएगा, this whole thing divided by some denominator square, it will be 0. So if I solve it further, I have 2 times 1 minus d square minus this becomes VDC into 1 minus d whole square minus VDC into R by R is equal to 0. So this becomes, I've just solved it, in shorter steps in my mind mostly, but you can simply, differentiate this and equate it to 0 and solve it on your own. You should get the same thing. So you have 1 minus D is equal to under root of R by R. So duty ratio max is equal to 1 minus under root of R by R. So at this duty ratio, your converter, at this particular duty ratio, your converter will give you the maximum output voltage. And what will be that maximum output voltage? Substitute D max over here. You will get V naught max is equal to 1 minus D is equal to R upon R. So VDC under root R upon R divided by R upon R plus R upon R. So this is 2 times R upon R. So this becomes under root. This becomes VDC by 2 under root of R by R. So this is the maximum output voltage of the converter. Now 2 things I want you to see, this equation and this equation. It tells you that if the load resistance is much greater than the internal resistance, यानी कि आपका R by R ratio, capital R upon small r ratio high है, तो आपको कन्वर्टर से ज़्यादा वोल्टेज मिलेगी. और ये रेशियो हाई होने का मतलब है that this ratio is small, and when this is small, 1 minus this is big. यानी कि हाई R by R ratios पे आपको हाई वोल्टेज मिलेगी at higher D max. So let's plot this. Let's plot it and analyze it a little more. It means that as you vary the duty ratio, your curve will look like this, something like this, and at D equal to 1, it will hit a 0. This is your boost converter curve, and your input is VDC upon, what was the input? VDC upon 1 plus R by R, right? अब आपने R by R रेशियो जब इंक्रीज किया, कैपिटल R by R रेशियो जब आपने इंक्रीज किया, तो आपको D max लेटर मिलेगा, यानी कि दिस वॉज योर D max वंस, and now as you have increased your R by R ratio, your D max will happen somewhere ahead, say somewhere here, and आपको वोल्टेज भी ज़्यादा मिलेगी कन्वर्टर से, तो आपको यहाँ पे कुछ वोल्टेज मिलेगी. सो दैट्स हाउ योर कन्वर्टर कर्व विल चेंज. इनफैक्ट आपका स्टार्टिंग पॉइंट भी कर्व का चेंज होगा इफ़ यू सी दैट. तो दिस इज़ वन पॉइंट, दिस इज़ अनदर पॉइंट, and if you increase R by, you're decreasing this, and if you're decreasing this, you're actually increasing the output voltage. Yeah, so VDC R by R, this thing will also increase, so your curve will become this. Your D max has moved from here to here, and your output voltage from the converter has also increased from here to here, right? And even your starting point voltage has also increased. यानी कि जितनी ज़्यादा लोड की रेजिस्टेंस होगी with respect to your internal resistance of the inductor, your curve will become, you know, better and better in terms of boosting. ये आपको स्टार्ट में भी ज़्यादा वोल्टेज देगा, बाद में भी ज़्यादा वोल्टेज देगा, और आपका D max closer and closer towards 1 होगा. And the most ideal condition is when D max is equal to 1 and your output voltage of the converter itself is equal to infinite. That's your ideal case. So this was about the non-ideal boost converter. I'll give you some questions on the WhatsApp group, and we can maybe now hold a doubt clearing session about these converters. So please try to solve those questions. I hope this was I hope I could, you know, convey all that I wanted to convey to you through this lecture. Please give me your feedback, and if you have any queries, we can communicate through the group or through a doubt clearing session. Wishing you all the best. Keep me posted.